we're going to talk about some very early examples of solving second-order linear homogeneous differential equations. Here we'll start with an initial value problem. Where we have this very simple differential equation, y double prime plus y equals 0, with the initial condition that y of 0 is 1 and y prime of 0 is 19. Now, this is a differential equation, which is very simple, and we should be able to just guess solutions. So I'm just going to write down solutions, sine t and cosine t, and I claim that you can check in a matter of seconds that these are both solutions. How might you guess it? Well, something you probably remember from Calc 1, that when you differentiate the sine function twice, you get minus sine t. You add that to the original function y, which is sine t, you get 0. And the same is true for cosine. So even though we haven't learned any method of finding this, it's pretty obvious now that sine t and cosine t will actually work. These are two particular solutions. Now, what we learned is that once we have any two solutions, all linear combinations of these solutions are also solutions. So any function y of t equals c1 times sine t plus c2 cosine t, c1 and c2 are just any real constants, will also be a solution. How does that help us? Well, I'm looking to find a solution with y of 0 equals 1 and y prime of 0 equals 19. So for my solutions that are just of this form, what is y of 0? Y of 0 is c1 times sine of 0, which is 0, plus c2 times cosine of 0. Cosine of 0 is 1, so that just gives me c2. That tells me c2 must be y of 0 is 1. C2 must be 1. What is y prime of t? Y prime of t is c1 cosine t minus c2 sine t. So then when I plug in 0, I see y prime of 0 is c1 times 1 minus c2 times 0. So that's just c1. And y prime of 0 has to be 19. So c1 must be 19. In other words, to solve our initial value problem, we have a solution, y of t equals c1, which is 19 sine t plus c2, which is 1, times cosine t. Now you should double check this. For this function y, compute y double prime, add it to y, and I'll let you do it. You can probably do it in your head, but you can do it on a piece of scratch paper as well. Check that y double prime plus y really is 0. And then you check also that the initial condition is satisfied. It's immediate. If you plug in 0, y of 0 will be 1. And on quick differentiation, you'll see y prime of 0 really is 19. Now here's the basic idea that we want to move towards. I would like to be able to say y of t equals c1 sine t plus c2 cosine t is what we'll call the general solution. In other words, I'd like to say not just that every function of this form is a solution, which we know is true, because sine t and cosine t were easily seen to be solutions. Also, you could check it directly. But I'd like to say every solution is of this form. And we really can't say that. The reason we can say that is from our general existence and uniqueness theorem. If you give me any initial condition, say y of 0 equals y naught and y prime of 0 equals y naught prime, I claim you can easily solve uniquely for C1 and C2 that makes that true. And not just if you have y of 0 equals y naught and y prime of 0 equals y naught prime, but even if you had an initial condition located somewhere other than 0, you can easily use this just by direct computation, solve for C1 and C2 that make this true. Thus, by uniqueness of solutions to the initial value problem, really every solution has to have this form, because for solutions of this form, I can solve every possible initial value problem. So I really have all the solutions here, even though that might not have been obvious when we first wrote it down, and this will be the unique solution to the differential equation that satisfies this particular initial condition. Let's look at a totally different type of problem. Not totally different, there are some similarities, of course. In fact, it looks like the previous one's a special case here. I want to look at, in general, second order linear homogeneous differential equations with constant coefficients. In other words, the coefficient functions here, a, b, and c, are constants. I know for our general form we had 1 times y double prime, so we could divide out by the a, but for reasons you'll see later, it's nice to allow a constant here, which doesn't harm anything. So we have a constant a times y double prime plus b times y prime plus cy equals 0. This is a homogeneous, I should have said, second order constant coefficient, homogeneous differential equation, because I still have a 0 here on the right side. And now I'd like to guess one type of solution. And I'm going to guess solutions that are of the form y equals e to the rt. You might wonder why we're guessing solutions of this form, but you'll see these functions are simple to work with, and you'll see very quickly why they provide a nice class of solutions that will be of interest to us. So bear with me as we just ask, what if I have a solution of this form? Will any number r work? Well, we'll just compute for this function y, we'll compute y prime and y double prime. That's easy. Y prime would be r e to the rt. Y double prime is r squared e to the rt. And then we'll plug that back in there. Ay double prime would be a r squared e to the rt. Plus by prime gives us plus b r e to the rt. Plus cy is c times e to the rt equals 0. So our differential equation here, when we plug in this function y equals e to the rt, gives us this equation. Now you notice e to the rt appears in all of these terms, and e to the rt is never 0. So I can just divide through by e to the rt, and what I'm left with is this quadratic equation, ar squared plus br plus c, and we give that equation the name, the characteristic equation. The reason for that is, based on what we've just done, if r is a solution to this equation, this characteristic equation, then e to the rt is a solution to ay double prime, to this equation above here, which I'll rewrite, ay double prime plus by prime plus cy equals 0. So this gives us a way to find special solutions that are of this form, e to the rt. Now, we won't prove this right now, but just as in the previous problem, if I can find two solutions, and they'll have to be what we call independent solutions, but bear with me, we'll get to that in just a day or two, what we mean by independent solutions. If I can find two fundamentally different and linearly independent solutions to this differential equation, then we'll be able to say something very similar to what we said before, that the set of all linear combinations of these solutions will be the full general solution to this differential equation. Finding solutions will depend on solving this equation. Of course, this is a quadratic equation, and everybody should remember how to solve a quadratic equation. How do we solve ar squared plus br plus c equals 0? We probably learned that in middle school or maybe in high school. You can solve that with the quadratic formula. Which says that the solution r is equal to minus b, this coefficient b here, plus or minus this thing, the square root of b squared minus 4ac all over 2a. So we have the plus and the minus. That means if we just use the plus here, we'll get one solution. If we use the minus, we'll get another solution. Of course, we have to be careful here about what's under the square root. So there'll be several different cases, and over the next week or so, we'll discuss what's going on in the different cases, because it will be important for us to solve second-order linear constant coefficient homogeneous differential equations. But for now, let's just look at an example. Let's see what we want to solve this. It's a second-order linear constant coefficient homogeneous differential equation. So that's a lot to say, but you want to get used to saying that whole thing. This differential equation, y double prime minus 3y prime plus 2y equals 0, has a characteristic equation which is just r squared minus 3r plus 2 equals 0. We can use the quadratic formula to find the solutions to this equation. Alternatively, all of you, I'm sure, know very well that we could just factor the left side as r minus 1 times r minus 2 equals 0, which immediately tells us that one of these factors has to be 0 at least, which means r is 1 or r is 2. So we have these two roots to the differential equation. And what does that tell us? That tells us we have two solutions that we know of now for the differential equation, and that is, I'll call them y1 equals e to the 1 times t, and y2 equals e to the 2 times t. These are solutions. And you should definitely always be willing to check that. Plug in e to the t, where it's very easy to check. Y double prime is e to the t, then you subtract 3 times y prime, which is, again, e to the t. So you have e to the t minus 3 e to the t plus 2 e to the t. That really is 0. And check that the same thing is true for e to the 2t. Now, I have these two solutions. What if I actually wanted to solve the initial value problem, which had that same differential equation with now our initial condition? Y of 0 is 1, and y prime of 0 equals 2. How would I do that? Well, I know any linear combination, I'll call it y of t, an arbitrary linear combination, c1 e to the t plus c2 e to the 2t, is also a solution. Anytime I have two solutions to a linear homogeneous differential equation, here it's a linear second-order homogeneous differential equation, but the same thing will actually be true, as we'll see later, even for higher-order linear homogeneous differential equations. Anytime we have two solutions, all linear combinations of them are still solutions. So this is a solution for any constant c1 and c2. And then, of course, from this y of 0, when I just plug in t equals 0, I get c1 times 1 plus c2 times 1. So I get c1 plus c2. And so we need c1 plus c2, that's y of 0. That should be 1 from this first part of the initial condition. And then if I compute y prime of t, that's c1 e to the t plus 2c2 e to the 2t, so that y prime of 0 is now c1 plus 2c2, and I need y prime of 0 to be 2, so I need c1 plus 2c2 equals 2. So in essence, we need to solve this system of regular old linear equations. And all of you know very easily how to solve systems of linear equations. This is only two linear equations and two unknowns, and it's a very simple one. The easiest way to solve this system is to take the second equation minus the first equation, and we immediately get c2 equals 1. And when c2 is 1, the first equation or the second equation tells us immediately c1 is 0. Thus, if c2 is 1 and c1 is 0, y of t equals 0 times e to the t plus 1 times e to the 2t. In other words, y of t is just e to the 2t. That function by itself. Yay. You can check this function is a solution to the differential equation here. And this function also satisfies the initial conditions. And just like before, we see that since we have these two solutions, and we'll always be able to solve no matter what constants, if I put a y naught here and y naught prime, whatever constants I put there, I'd be able to solve this system of two linear equations and two unknowns. I'd be able to solve any initial value problem with this differential equation. In other words, given any different initial conditions and the same differential equation, I could pick C1 and C2 to get a legitimate solution to the initial value problem, which by our existence and uniqueness theorem should be unique. Thus, I must have every possible solution. In other words, this is the general solution to my differential equation. If there are any solutions of different forms, then there would be some initial value problem which had a solution very different from the one that I would get in this manner, and that can't happen because of the existence and uniqueness theorem. So where are we going to go from here? Well, in order to have enough flexibility with these two constants to be able to solve any initial value problem, I really needed two independent solutions here. We had no problem with that because our characteristic equation, this is the characteristic equation here, had two distinct roots, r equals 1 and r equals 2. But here's something you all know about quadratic equations. Not all of them have two distinct roots. Some have a single repeated root, and some have no roots at all when we're talking about real numbers. So we're going to have to deal with other situations where we don't get enough solutions that are of this special and very simple form. And we'll be talking about those cases over the next week or two.